Okay, so let us continue our discussion of describing error for the target function, right? So we have characterized target function in terms of the complexity and then the noise that is usually accompanied with the target functions, rather embedded in the target function. So now we're talking about error, and this error is usually user defined, I would say, because it depends on the context of the problem domain, and the user, like what error makes more sense to the application. And in order to illustrate that, what we're doing is we are looking at a fingerprint recognition system or a fingerprint recognition application. Let's say I have like this input where there is like a fingerprint of somebody, right? And that's my input data, that is my X, right? And then based on my learning algorithm, and the entire like learning problem setup, I eventually am able to come up with my final hypothesis G. And this G, and let's assume this is a classification problem. So basically I'm trying to identify whether this is the right person or not. So this is more of a classification problem. And what this G is doing, it's categorizing the outcome as a yes or a no. So basically, yes, this is the correct person for whatever application, or no, this is not the right person. Now, let's try to utilize this fingerprint recognition system for two different situations. The first situation that we're looking at, and let me draw this here, is the supermarket situation or the supermarket application, right? And what we are doing here is that the supermarket is basically taking fingerprints of the customers, and based on like whoever is eligible for a discount or a coupon, they're giving them that, right? So now in terms of the error, what can go wrong? So the first thing that can go wrong is that you can, or the supermarket can say no. So they can say no to the right person, right? So they can do that. That's one possibility, to the right person. Now the outcome of that, like let's say I am eligible for a discount and they said, no, we could not, my system is not able to recognize this. And so they deny that. And the worst that can happen is that like the customer can get really angry, and then they can look for some other business and maybe never come back to the supermarket, right? So in terms of the error that was encountered as a result of this application, is that it is quite costly for the supermarket, right? So it is costly, I would say it matters a lot to the supermarket. So it's costly for the supermarket. Let me write a short for supermarket SM, right? So saying no to the right person is really, really costly because that person is never going to come back. So you're losing business. Now, another possibility is that the application or the outcome can say yes to the wrong person. So somebody who wasn't eligible for the discount or the coupon, whatever it was, will get it, right? And chances are high that they might just like not take it, or even if they take it, from the perspective of the supermarket, this is not costly, or maybe we can say that this is okay, right? So not costly as much, or maybe even up to a certain extent, this error is kind of okay. This is acceptable, right? Because they're not really losing out on anything. So this was the application of the fingerprinting recognition system in a supermarket. Now there can be another sort of use of this fingerprint recognition system, and that could be in CIA access control, right? So there is this access control where people who work for CIA can enter a building maybe, or people who work at CIA have the access to a particular um, whatever, right? So basically that's the access control that CIA is using. So basically they're trying to use this fingerprint recognition to know whether this is an employee or an authorized personnel or not. Okay. So again, the same two things can happen. Now the first thing is if I say yes to the wrong person, so let's say this application says yes to the wrong person, you can just tell that this is going to be extremely costly for a place like CIA, right? So this is extremely costly, not just costly, it can be a disaster, right? So extremely costly for CIA because they're letting in somebody who wasn't authorized to enter a certain building, right? And the second one is if I say no to the right person, which means that the system said no or denied access to somebody who was an employee. Well, from the perspective of CIA, this is kind of okay. It's not as bad because there must be some other way of identifying that this is an employee, and that the employee can insist that, okay, no, I already work here and this is my other credentials, and based on that, maybe take the fingerprint again, and eventually they will get the right solution to that, right? So this is okay. This is not a huge cost. Now, if you look at the supermarket situation again here, when we said saying no to the right person is costly for the supermarket, this particular situation is known as the false negative, right? You said no, which was like negative, and to the right person. So this is a false negative. And when we said yes to the wrong person, it wasn't obviously costly at all, but this situation is also known as a false positive. Both are errors, but like it depends on the application which one is costlier than the other, right? Both are errors, of course. But here for CIA, saying yes to the wrong person is a false positive. So slight, and in saying no to the right person, as we know, is a false negative. Okay, so this is one way of illustrating that the same error can be more fatal for a certain situation as compared to the other, right? So a false positive was fatal for the CIA access control system, and a false negative was bad or like really costly for the supermarket situation. So let's try to interpret what we are trying to do, because we said that when we're trying to characterize the error for a target function, what essentially I'm trying to do is that I'm trying to define it in terms of like whatever the application is. So basically errors are not good, right? So in order to interpret it, this is like not good for us, for any application. But how much not good it is totally depends on the problem domain, right? So what we'll do is we will penalize only when like the mistake is made, and the magnitude of that penalty will depend on the application. Okay, so there is a way of interpreting the error, and this is known as the risk matrix. And I'm going to draw it for both for the supermarket problem and the CIA problem. So let's look at the supermarket problem first. Now, remember what this like fingerprinting application is doing. We have a G that is predicting a yes or a no, right? But then there is reality, right? So this essentially risk matrix is a sort of a comparison of like what is true in reality and what is that G is predicting, right? So this is G and this is reality. And let me just create this table. This is a yes and this is a no. This is a yes and this is a no. Right. So as I said, we penalize only when there is a mistake that's made, otherwise everything is good. So basically we are trying to characterize or basically come up with quantify, basically we're trying to quantify the error in some measurable way. So let's say we have a number to quantify that. So of course that penalty or that number is going to be 0 in these two cases, because look, the reality said yes, and my G also said yes. So it confirms to the reality. Similarly, it said no, reality said no, and my G also said no, so confirms. And so there is no penalty there. Now, I want to penalize, but this is the supermarket case. And let me actually write down the risk matrix for supermarket. And I have a risk matrix for the CIA. Okay, so if you remember, for the supermarket, we said saying no to the right person is really, really costly for the supermarket, which means the false negative should have a higher penalty. So let's assume I decided it's 10, right? And then saying yes to the wrong person is not as costly, right? So that means the false positive is not as costly. So maybe the magnitude of that penalty is going to be 1. Similar to that here, coming here, what we can say for CIA is slightly different from what we said here. So this is my G, and this stays as my reality, and it's like this. This is a yes, no, yes, no. Now, if you remember, now saying yes to the wrong person was a disaster for CIA, and so they will look at it like with really, really they will be like really cautious in that situation, and they don't want that to happen. And so what they'll do is they will like really penalize that false positive, right, with a very high magnitude. So maybe 1,000, right? And then again, this is user defined. This could be anything depending on the problem domain. So it could be like 1,000. And this one here would be small because saying no to the right person wasn't that costly. And eventually they can come up with the fact that, yeah, this is our employee and let them in somehow, right? So this was one. So basically what this kind of summarizes is that the interpretation of error basically depends on the problem domain and the user. And this is how we characterize it. Now, putting it in more sort of a definition way, like how do we define errors generally when we are studying machine learning problems, that is called a pointwise error. So in general, errors are classified as pointwise errors. And basically, it's nothing but a function. So a pointwise error is a function of h of x, right? X is my final test point, and y, which was the actual outcome. So in general, this is what my pointwise error is going to be. And the value of this pointwise error will be decided in a variety of different forms, variety of different ways, depending on what problem you're looking at. For example, until now, we've looked at the classification problems. So the four classification problems, what we have is known as binary errors. Okay, what are these binary errors? Basically, this pointwise error is taken, and then it should quantify the amount of price you will pay when my h of x does not conform to my y, right? The calculated value of my outcome, right, does not conform to the actual outcome that I have, the actual example I have. And my pointwise error is going to count all such instances, right, whenever there was a disagreement between h of x and y, right? So this is mostly used for classification problems. Let me write that down. Classification problems. And the way we write it mathematically is that for binary errors, e h of x, y is basically the indicator function. So indicator function is nothing but really a count of this yes or no of the disagreement, because remember this is, okay, this has to be y. This inside is the indicator function, just so that does not create any confusion. This is the indicator function, and we are counting essentially the disagreements, right? Okay, the second form of any pointwise error is mostly for regression problems, and this is also known as squared error. So squared error for regression problems, that means when the outcome is continuous, unlike classification problems. And so one way of sort of quantifying the pointwise error is that h of x, y is going to be the squared difference between h of x and y squared. Okay, so this is basically for regression problems. The thing is that the entire theory that we have derived until now works for both definitions. We can define the in-sample error and the out-of-sample error for all these pointwise errors, as long as we have a reasonable bound. And what that means is, as long as we know that we have this function well behaved to a certain extent, right? So how can we do that? Well, in order to write the in-sample error for hypothesis H, it's nothing but this average of all these pointwise errors defined for all like points that I have in my sample, I from 1 up to n, and then this is going to be the sum of all the pointwise errors which are defined for all i's and yi, right? So this is my in-sample error. Out of sample error is slightly more, I would say, complicated, but not really, because if you think about it, we don't know much about it because it's in the actual outside data, but we do know the expected value of things, right? So the entire expectation over x of this entire like pointwise error, whatever it is, whatever the problem we are solving, and f of x, because of course this is out of sample error. So this expectation of the pointwise errors is what characterizes my out of sample error. Now, again, to summarize, the error measure that you choose will impact the algorithm that does the picking, right? Because if you remember the two-step process, we are trying to pick a hypothesis based on E in that is dependent on my pointwise error, and then that in turn is dependent on like how you're selecting things. And so that's why whatever error measure you're going to use will impact my algorithm. Okay, so having said that, let's actually put everything together for the learning setup. Now this entire picture is known as the learning setup along with the two-step process. So let me first summarize that. This is the learning setup. Now a few things have been added. If you remember, we fixed the hypothesis set before we look at the data, so that's all fine. That feeds into my learning algorithm here, and then the data that we are getting is from a distribution. So we have like this thing that's added to what we saw earlier, right? Although it can be an unknown distribution, right? P of x, but both the training examples and my test comes from the same distribution. So that's one. And the way we're getting the training examples is obviously independent and identically distributed, which is IID. Right, so just to remind what we already said. Now, because the theory can accommodate a generic form of f, therefore it is a distribution now. Right, so earlier we had a deterministic form of the function f. Now we discussed f, and we know that f can definitely have some noise, and also it's derived, right, in a certain way that it is like more of a generic form, and so we are like keeping it in that most generic form, which is a distribution, right? So it has like the target function plus noise basically gives it or renders it this form. Okay, so that's the addition to what we already know. Okay, so this is taken care of. Now coming to the error measure and how is this contributing to g of x and the learning algorithm? Well, the learning setup, as I said, is this entire process plus the two-step process. So let me again write that down. Plus the two-step process. The first one was E out of G is almost equal to E in of G. And the second one was that my E in is almost equal to 0. Now what's happening is like whatever error measure we have decided, let's say this is a classification problem and my error measure is like the binary error classifier, whatever that is. So based on that, I'm going to try to get E in almost equal to 0 because E in definitely depends on my pointwise error, right? And then if I'm not able to do that, then I'll go back here and then maybe based on like until I get this E in really small, I can pick up an updated G, right? So basically the flowchart determines the process, right? And this is actually showing you what's happening. The learning algorithm is actually impacted by the error measure that I decided, because basically the final hypotheses will be picked up using the learning algorithm based on whatever my error measure is, because I'm trying to achieve this and theoretically achieve this, right? So in theory, we are trying to get this point number one. But next, what's happening is we are computing E in, right? And if it's not close to 0, then we go back to picking G until we get the best, right? And in addition to all of that, we also incorporate and always remember that there will be a chance of failure. There's always a possibility of failure. So together with the two-step process and also the assumption that there can be a failure or will be or maybe can be a failure, that's an equal possibility. Along with this entire process shown on the right hand side, this entire picture basically tells us or gives us the entire learning setup that we'll be using throughout going forward. Okay, so this actually answers our big question for this lecture. That was that yes, learning is feasible, and the way it is feasible is via this two-step process. This is the larger picture of how things fit into our learning problem. And eventually we are trying to get G, which we'll pick from using a learning algorithm, and the error measure from our hypothesis set, which was selected before we saw the training examples. And finally, try to come as close to F as possible. And again, a few things that we've added in this lecture are that this is target function is essentially a target distribution now, and the way the data has been generated is from an input distribution that is IID, which is independent identically distributed. Sorry. Yeah, so with that, I end this lecture. Thank you.